Okay, so hello everyone. I'm Lisa Stewart, Chief Administrative Officer at the Kavli Institute for Theoretical Physics. It's my honor to welcome you for today's talk by Dr. Charles Brown for the National Society of Black Physicists Innovate Seminar Series. Today's talk will be about 30 minutes and will be presented in webinar format. All questions will be held until the end. Please enter any questions you have for our speaker today into the Q&A section, and following the talk, he will try to address them as the time permits. Next up, I'd like to introduce you to Farah Simpson, the student representative on NSBP's board and also the leader of the NSBP Student Council, which is the group responsible for creating and leading this Innovate Seminar Series. Thank you.
Hello, everyone. I'd like to welcome you all back to the NSBP Innovate Seminar Series. I'd also like to take this time to thank you all for supporting our series thus far. For student council members, this is more than just a series of talks. We have not had the privilege of being able to engage with the research of physicists who look like us very often, and so we'll continue to hold this space for Black physicists. I hope that you all continue to enjoy our talks. Today is particularly special. It's our first postdoc speaking. And now I'd like to introduce you to the president of the National Society of Black Physicists, Dr. Stefan Alexander.
Hi, everyone. Yes, it's a real pleasure, a special pleasure to introduce what I consider to be one of our exemplar members of NSBP, who's also been very active, especially in mentoring others in our community. But he's also quite an excellent physicist. And my prediction is one day he'll end up being a president of the National Society of Black Physicists. This will be recorded. And so Charles, you know, I await my present for being correct one day. So Dr. Charles Brown is an experimental quantum physicist, science communication and champion for increased Black American representation in physics. Charles earned his bachelor's with honors in physics at the University of Minnesota, Twin Cities, and followed with his Ph.D. In physics at Yale University, where actually the very first Ph.D. of any field, including physics, was earned by Dr. Edward Boucher. He conducted experiments at superfluid helium, and he is now a postdoctoral scholar and Ford Foundation Fellow at the University of California, Berkeley. Charles has a long history of both empowering students, spanning the elementary through graduate levels, to pursue their STEM interests and advocating for the interests of Black students. Charles recently wrote a widely read op-ed, and I actually read it myself, about Black underrepresentation in physics that appeared in Physics Today, which has been sparking important conversations regarding necessary changes in the physics community. So with those words, I present Dr. Charles Brown.
Hey, thank you everyone for inviting me. I really appreciate this opportunity to meet with you all virtually and tell you about our recent work. So let me share my screen. Okay, so today, I'm going to tell you about interacting bosons in the flat band of an optical Kagome lattice. Now, I realize that sounds like a mouthful. It is. It's a very meaty topic, but you know, I do understand that this is, you know, a talk that's meant for a large audience, with, you know, attendees of various rank and various familiarity with these concepts. And so, you know, I have a few points in here for any experts that may be watching, but also, you know, I've really tried to explain some of the base concepts that hit at each point of the title. And so I'll explain sort of what all of the things in the title mean as I go on. Okay, so there we go. Geometric frustration in exotic states of matter. As it turns out, this concept of geometric frustration is intimately tied, or at least it can be intimately tied, to the creation and study of exotic states of matter. These states of matter that really necessarily need to be described by quantum mechanics, because quantum mechanics is sort of completely relevant in a way that no classical description can can describe the properties of this state of matter. Okay, so one definition of frustration can be the conflicting interatomic forces that make unclear what the lowest energy state of a system of particles is. And so I have a couple examples for you of frustrated systems. First, let's talk about magnetic frustration. Here I have an equilateral triangle where I can put particles at any one of the vertices. And so it's magnetism, and so I'm going to talk about particles with spin, intrinsic angular momentum. And it's just important to know that spin can be up or spin can be down. And in this system, the system will minimize its energy, which is what it wants to do, when the spins are anti-aligned. Okay, and so if I put a spin up at this location, and I put a spin down at this location, then what orientation should the spin at the top of the triangle have in order for the system to minimize its energy? Right? If we put a spin up at the top of the triangle, then the interaction between the top spin and the left spin is not minimal. If we put a spin down at the top, the interaction between the top spin and the right spin is not minimal. Right? So there is a confusion. There's a frustration here. What is the lowest energy state of the system? Right? It becomes unclear. There becomes several lowest energy states that are equally low. Okay? Another example of frustration is orbital frustration associated with motion of particles. And so here's a separate example where instead of a triangular configuration of particles, I have a cubic configuration of particles, where the particles can actually be at any one of the vertices of the cube. Right? The red arrows that I'm showing here, this is actually a figure taken from this paper, but the red arrows here are the net angular momentum of the particles at these positions. And it turns out that you can have this equivalent effect where it becomes unclear based off of the orientation of these angular momentum vectors, what is the lowest energy state of the system. You can actually have very, very many, and it turns out to be something else, namely interatomic interactions that push the system into picking one of these states. And so our goal is to study the physics of orbital frustration and I guess more specifically, how it leads to exotic states of matter. And our method to do this is by creating a Bose-Einstein condensate and putting it in a lattice that causes orbital frustration. Okay, and so I wanted to say a bit about frustrated lattices. Two particularly interesting, I think. Frustrated lattices are the Lieb lattice and the Kagome lattice. I took this image from this publication here, where the authors provide a really nice demonstration, or they provide a very nice description of the very interesting physics that one can study, both theoretically and experimentally in lattices that have this frustration aspect. Okay, and so when you look at these two lattices, you see the Lieb lattice on the left, the Kagome lattice on the right. The colored circles are where the particles can be, and particles are free to hop from site to site. And so here I have a green circle next to a red circle, and you see there's this parameter J that tells you something about the hopping. It doesn't matter what that is, but just know that particles can hop from colored circle to colored circle. And so when we look at these two lattices, we see that they're different, right? The one on the left looks like a series of squares, the one on the right, something like a series of triangles. And they share some very unique properties, I'll just say. These down here are band structures, and I'll say what that is later, but just know that both these lattices that have frustration have various interesting aspects, such as a flat energy band. Right? They both have this flat energy band, and I'm going to say more about that. That's sort of what this whole talk is about a flat energy band. I'd also like to point out to you that I'm telling you about these new results from a paper that we published. It just came out in PRL about a week or two ago now, where we see that interactions between atoms change this band structure. Right? Again, I'll tell you what that is, but it changes the band structure. And Ozawa et al. Actually saw similar physics in an optical version of the Lieb lattice. Right? So and now we've sort of confirmed this interaction-driven change in an optical Kagome lattice. Okay, but now, I just want to kind of hit home the point before I, start moving further and get to some of the more fundamental aspects of the talk. we are interested in orbital geometric frustration in the Kagome lattice. And so what do I mean by orbital? Well, here I'm referring to atomic motion, right? Motion of atoms. And by geometric frustration, I'm referring to the phenomenon of having a large number of low energy states, of ground states, where it becomes really unclear which state the system will fall into. And we'll see that, you know, interactions can coax the system to fall into a particular state. And it turns out that, you know, in the future, this will be an interesting way for us to push a system into some exotic state of matter that we can study. Okay, and so here's the Kagome lattice. I haven't said anything about the structure of the lattice yet. We see that it has some triangle structure. It turns out that the Kagome lattice can be represented by a series of these equilateral triangles that are connected by their vertices, right? We see that they all share a vertex, with this hexagon shape in the middle. For any experts that may be on the call, you know, one thing that's interesting is, you know, the condensate phase can flip sign as you go around this hexagon here. And so this leads to interesting things like vorticity and all these other, you know, cool features you might see in these states of matter. And so the reason why we like the Kagome lattice, again, is because it has a flat band. What I'm showing here is a plot of the energy versus the momentum of particles in the lattice, right? And what we see are these bands here. We see one here, we see another one here in the blue, we see another one that's flat, and then we see one all the way up here. And so just know that when you have particles in a lattice, if the lattice is particularly deep or sufficiently deep, you only have a certain group of energy levels that your particles can exist in, right? And one of those groups of energy levels is this flat band. And it is this flat band that allows us to push into a system that has geometric frustration, right? Because in the flat band, all of our particles have the same motional state. They have the same energy state, right? And so this gives us a way to study physics in a system where you have many particles, at least, you know, in the future, you have many particles that are interacting with each other, where interactions can drive the system into some exotic state of matter. Okay. And so let me start by, I'm going to build up to our experimental results, but I want to start by introducing the different important aspects of the work. So I want to talk about the difference between bosons and fermions. There are, you know, different ways to classify different types of particles. One particularly relevant here is bosons versus fermions, where bosons are particles that have a net intrinsic angular momentum that is equal to an integer, whereas fermions have half integer intrinsic angular momentum. And so in this cartoon, this drawing that I'm showing you, we have a group of bosons and fermions trapped in the same harmonic potential, right? So by that, I just mean that they are in a potential energy landscape where the potential energy increases with the distance squared as you move away from the minimum. We also know from quantum mechanics that particles in a harmonic potential have these quantized energy levels, where the particles can have this energy, or this energy, or this energy, and so on. But it can't have any energies other than the values that or the levels that I'm showing here. And the striking difference between bosons and fermions is, even at zero temperature, even at absolute zero temperature, bosons are happy to pile up on each other and be in the same state. They can be in the same quantum state, and that's perfectly fine. But due to Pauli exclusion, fermions can't pile up in the same state, right? So you can try to put all the fermions into this lowest energy state, but they don't like that. They will stack up and fill up a certain level of these energy states that are available in the potential. Okay, that's the important difference. Bosons, we can pile all the bosons into the lowest energy state, and they're happy to be there. And in our experiment, we use the bosonic isotope of rubidium-87, to make a Bose-Einstein condensate. So I'll say a bit about what that is. And the Bose-Einstein condensate in itself is an exotic state of matter. A particularly good way to think about a Bose-Einstein condensate and when you might get one is by thinking about the de Broglie wavelength. Right, so the de Broglie wavelength describes the wave-like behavior of matter. Right, all matter has some wave nature to it. It just turns out that decoherence, interactions with the environment, make that wave-like behavior go away. And so in this expression here, I just want to point out the fact that this de Broglie wavelength is inversely proportional to the mass and the temperature, right? So as the mass of your object gets greater, the de Broglie wavelength becomes less. As the temperature gets greater, as things get hotter, the de Broglie wavelength becomes less. And so in a sense, that sort of pushes you away from being in a region defined by quantum mechanics, right? So if you can make the mass really small and you can make your system really cold, then your de Broglie wavelength can become pretty large. And, as it turns out, if you can get your temperature low enough, you can actually have the volume associated with your de Broglie wavelength, lambda cubed, to be greater than the average volume taken up by a particle, right? This is the regime where the wave function associated with each of the particles in your system, they start to significantly overlap with each other. And then at that point, the only way to describe the system is quantum mechanics, and you get a lot of really interesting features out of this. And so I'm showing a picture here that I took from the NIST website and associated with Agila and the University of Colorado Boulder, where they created a Bose-Einstein condensate in the lab. So here they have a sort of normal gas. It's a cold gas, but it's a normal gas. And as they cool it, the gas starts to fall into this really unique condensate, this Bose-Einstein condensate, characterized by having essentially all the atoms in the lowest energy state associated with this point here, zero momentum, right? So this is a detection, verification of having a Bose-Einstein condensate that they actually take by measuring the velocity of these particles. Okay, so I wanted to quickly bring up the Schrodinger equation. The Schrodinger equation in quantum mechanics is an incredibly useful equation that allows you to extract useful, properties of your system, for example, position and momentum. And so here I've showed you the time-independent Schrodinger equation. There's no time, right? And it has two important parts. It has a kinetic energy term. So this term multiplied by the wave function psi tells you about the kinetic energy. This term multiplied by psi tells you about the potential energy. And that gives you the total energy of your system, of your particle. But in order to describe Bose-Einstein condensates where the particles interact with each other, you need to actually modify the Schrodinger equation to look like this. And this is referred to as the Gross-Pitevsky equation that has this additional term that tells you about the strength of the scattering of the interaction between, particles in the Bose-Einstein condensate. But also it depends on this term here, psi squared, right? So now this is a differential equation, right? These derivatives appear, but now this differential equation is nonlinear in psi. And that actually manifests quite a lot of interesting physics. But I also want to point out that this parameter psi squared, it tells you the density of your system. And so we see that the density plays a part into how the system evolves. The density determines what this wave function is, and this wave function determines the properties of the system. And so as you change the density, know that you will change property of the system. That's important for going forward. And I just wanted to include a picture of a VC from our group. So this is a picture of a Bose-Einstein condensate here in the red, characterized by having all these atoms in the same, lowest energy state. The temperature is around 50 nanokelvin, right? That's a tiny, tiny fraction, of order 10 billionths of a degree above absolute zero. And as far as we know, Bose-Einstein condensates are the coldest states of matter in the universe. Okay, so now I'm going to tell you about lattices. I think at the most simple level, you can just think of a lattice as a periodic set of points that has some set of symmetries. All right, so one lattice that we are, we sort of see around a lot, square grids, like graph paper or something. We just call this a square lattice. And if you look at it, you'll notice several things about it. One, it has translation symmetry. And so you can, and this is actually true of all lattices, all periodic lattices, which is what I'm going to talk about here. They have this translation symmetry. So if I take this point here, make a square around this circle, I can translate it up and I can translate it down, and I can make copies of it over and over again, and I just make the square lattice grow, right? So if I translate it by one of the distances you see between the points, the lattice looks the same. You also see that if I rotate the square by 90 degrees, if I rotate the square lattice by 90 degrees, the lattice looks the same. So it also has this 90-degree or fourfold rotation symmetry. All right, another lattice is the triangular lattice. Again, it has a rotational symmetry. It's actually 60 degrees instead. It also has translation symmetry. Another lattice, which I've already told you a little bit about, is the Kagome lattice, which has its own sets of symmetries. But what's common to all lattices, or at least all systems where there are particles, like real particles that are in the lattice, is that they have something called band structure. And so I'm showing just a nice little graphic of a one-dimensional system, right? These are two-dimensional lattices. So a one-dimensional lattice is basically just a series of points where a particle can, sort of hop between point to point. Now, normally, if you want to think about the energy of the particle, well, the energy of the particle, it's proportional to the momentum squared, right? Maybe what comes to mind is p squared over 2m for the kinetic energy. And so what I'm plotting here is effectively the energy of the particle in this 1D lattice versus its momentum, right? But this is for a lattice that is sort of as weak as possible. It effectively doesn't bind the atoms. And so what you see is the relationship you expect. You see something that's quadratic in the momentum, right? That's what we expect for the kinetic energy. However, if you start to change the lattice depth, the degree to which particles are confined to a certain set of points, if you increase it away from zero, then you find that the particles can only have energies that are in these energy bands, right? So only in the green region or the blue region or the red region can the particles exist. Like they can only have energy levels that exist in those regions. Okay, so that's important about particles and lattices. But I wanted to, tell you about how we actually make these optical lattices. And so mathematically, one thing that's really useful to think about are traveling waves. So in this GIF that I'm showing you, we have a blue traveling wave and a red traveling wave, and they are traveling towards each other, right? And so the net effect of these two waves, when they add up, is a standing wave that doesn't move, right? The standing wave is in the black. And we can do this experimentally with lasers. So you can describe a laser as a traveling wave, just like the blue or the red curves you see moving. It's just the traveling wave it's a traveling wave of electric field. Okay, and if I take a zoom in on this region where the lasers overlap, and I look at the time average of the electric field intensity, that is the time average of the black curve that I showed you, then you get something static that looks like this, where the atoms want to go to the regions where the electric field intensity is the lowest, right? And so this is how we can make a lattice. We can do this in one dimension and give these atoms essentially perfect spacing, right? This space is equal to this space, and we can do this over very large distances, and we can do this in multiple directions. So we can make a 1D lattice or a 2D lattice or a 3D lattice using this technique. And yeah, so that's just this point here. You can use multiple pairs of intersecting beams to make 2D or 3D lattices. And that's what I'll show you next. So this is how we make our optical Kagome lattice. We have 6 lasers in total. There are 3 green lasers, and there are 3 infrared lasers. We have the triplet of the green lasers intersect each other with this relative 120 degrees. And we overlap with that, basically a copy of that arrangement, but just made from lasers with that are infrared, with actually double the wavelength. And so if you perfectly overlap them with each other. And if you take a zoom in of this region where all 6 beams overlap, right here, what you find is a potential energy landscape that looks like this. So this is the Kagome lattice that I showed you. It's just rotated, where the atoms want to go to the black regions, the regions of minimal potential energy, right? That's where they want to go. So this is just rotated. This is one of the equilateral triangles here that I'm, tracing out with my mouse. Here's another one here. Here's another one here. So here's that 6-pointed star that I showed you earlier. It's just rotated to the side. This is our optical Kagome lattice. So I guess now I think I've told you, most of the important stuff for describing the experimental and theoretical foundations of the work that we're trying to do. And I just want to point out again that, the data that I'm going to be showing you is our work that was recently published in PRL. And it's down here, so I encourage you to check it out. So in order to do these experiments where we, put the Bose-Einstein condensate into the flat band, which from the diagram that I showed you is actually the third band, we need to apply forces to it. And so in order to apply the force, we take a laser beam and we offset it from our Bose-Einstein condensate. And this creates a force that wants to pull the Bose-Einstein condensate towards the center of the laser. And so if we want to give the BEC an acceleration, if we want to increase it up to some velocity, which allows us to put it into a particular energy band, all we do is pulse on this laser. It applies a force for the pulse time, and that will give our BEC some velocity. Okay, and so I wanted to show you this. This is a comparison of predictions on the top and experimental data on the bottom of what the Bose-Einstein condensate looks like when we put the condensate into the Kagome lattice. So I mentioned that there are multiple energy bands. Well, there are only 4 that we're going to talk about here. The sort of 4 most unique ones associated with the Kagome lattice. These 2 images are associated with the atoms being in the first energy band, the first band of allowable energies. The only difference is this one, in this one, the Bose-Einstein condensate was not accelerated, whereas in this one, we gave it some acceleration, and so it has some velocity when it went into the lattice. This image is a prediction for what images of the Bose-Einstein condensate looks like after we put it in the Kagome lattice in the third band, right? The flat band. And this one is a prediction for the fourth band. And so I just wanted to show that, this is what we predict the images to look like after we put the BEC into the lattice. And these are the images that we get out, right? So these agree very, very well. Just a testament to our sort of understanding quite a bit about our system and how Bose-Einstein condensates, which I described are very wave-like in nature, they diffract very much so like light does when light bends around objects, right? These are images of a Bose-Einstein condensate diffracting from the optical lattice that I mentioned to you. Okay, so now I want to tell you about the sort of most important measurement of our recent paper, and that is this one here. So the vertical axis is the group velocity of the atoms, which the Hellman-Feynman theorem tells us is the local slope of the energy band. And so if we can measure the atom's group velocity in the lattice, then we have a proxy for the energy band. We're effectively measuring the energy band. We're actually measuring its derivative, but it tells us about the band. And so I told you all this stuff about how the flat band should be flat. Well, that means if I can measure the flat band's derivative, then what I should be measuring is 0, okay? So what am I doing here? In this region, I am measuring the slope of the energy band of the first energy band, right? So this is the slope of the energy band versus the momentum of the particles in the lattice, of the atoms in the lattice. This is sort of what we expect, basically, for how the energy band changes shape, I guess, as you change momentum. The most important point here is this region, where we're looking at the slope of the energy band of the third energy band, right? This one should be flat. So if the band really was flat, instead of measuring non-zero, the blue data points, these are our measurements, we'll be measuring 0, right? So this tells us that the band is not flat, even though I said all the stuff about how the Kagome lattice gives you a flat band. And so just a bit more about what else is on the plot. The dotted line is a prediction, or the dashed line is a prediction from what normal band theory calculations tell you the curvature of the band should be. That's also not flat, but that's sort of a technical detail. It could be flat. It's just not how we presented it. But the solid line, we'll see that it actually agrees more with our data. And this is a prediction using the Gross-Pitevsky equation that I showed you earlier that takes into account interactions between particles. So this dashed line is sort of normal band theory that doesn't know anything about interactions between particles. The solid black line is the Gross-Patevsky equation solved on a lattice, which does know about interactions, and that is in better agreement with our data, much more so than the normal theory without interactions. Okay. So, you know, the question is, why is it that we don't see the Kagome lattice? What is actually going on? It turns out that the interactions among atoms, they like physically restructure the optical lattice. And then, you know, a more technical point is that it leads to this self-consistent band structure. But what's happening is the interactions between the atoms, they provide a contribution to the potential energy of the atoms. And so if the atoms can interact, then they can change what the effective potential is that they feel, right? There's some external potential imposed by all the intersecting lasers, and then there's this extra potential that comes from their interactions. And when you add the two together, they can actually make the atoms not see the Kagome lattice anymore. And so this plot, these two panels are showing you exactly this. I'm actually going to start with the one on the right. I didn't mention this before, but lattices have unit cells. They have this concept of unit cells, and it's actually the unit cell that you can move around. You can translate it around, and it'll allow you to generate the lattice or to replicate the lattice. The Kagome lattice has 4 sites technically, but really 3 are important: A, B, and C. These are the ones that actually have particles in them, and the D site is excluded. And what we see in the third band, this is taken in the third band, in the band that's supposed to be flat. We see that because of the interactions, basically all the atoms are distributed between 2 sites, sites B and C, when in the Kagome lattice, they should be distributed between sites C, B, and A, okay? And so on the left panel, this is a calculation of the distribution of atoms between these 4 sites. And we see that like where 1 is sort of all the atoms that are distributed between the 4 sites. What we see is versus the horizontal axis, which is sort of the strength of the lattice. This is how hard the particles are being bound to the lattice sites of what should have been the Kagome lattice. You see the atoms redistribute between sites B and C sort of equally. These are overlapping with each other, and sites A and D, where they have very, very small fraction in sites A and D. Okay, and so I just wanted to hit again the point that because of interactions between atoms, between these atoms, the effective potential that they see is no longer the Kagome lattice. And so in a sense, then it makes sense that we don't see a flat band, because a flat band in our system is specifically a property of the Kagome lattice. But I just wanted to add the point here that, you know, this nonlinear system we have, right, because of the psi squared that I showed you in the Gross-Patevsky equation, this has some surprising outcomes. For the experts that may be watching, this leads to swallowtails in the band structure, this nonlinear Landau-Zener effect, hysteresis, and symmetry breaking associated with how you approach different high symmetry points in the lattice. And there's a lot to explore there for sure. So lastly, I wanted to show you this plot, which is sort of more confirmation that what we're really seeing is lattices, an effect of interactions between atoms in the lattice. And so in this top plot, what I'm showing again is the local, what I'm showing again is the curvature of the flat band, of the should-be flat band, right? And I'm showing it as a function of how strong the lattice is. And so what we're seeing is, as I make this lattice stronger, we see that the curvature is changing. And why might that be happening? Well, as I make the lattice stronger, sort of more particles can hop into the different lattice sites and interact with each other, or less, depending on how strongly I can find the particles to the lattice points. And so if I can change the strength of the interactions by changing how tightly I can find the particles to the atoms to the lattice points, then I would expect the group velocity to change. This is exactly what we see. And I'll just point out that this black line, which is the Gross-Patevsky simulation on the lattice, agrees pretty well with the data that we measured, the blue circles. In particular, in compared to this dashed line, which is non-interaction theory, the normal band theory that doesn't know about interactions. Another example, another sort of proof of this is more direct, and I really like this measurement. This is, again, the curvature of the flat band, the should-be flat band, as a function of density, right? And so if we change the density of atoms in the lattice, which is a direct way to change the strength of the interactions between them, we see that the curvature is changing, right? So this is confirmation that, again, atom-atom interactions are changing the structure of the lattice away from the Kagome lattice, right? This is the reason why we are not seeing a flat band. Okay, and so I'll conclude here. I think I'm at about 36 minutes, so thanks for letting me go over by a little bit. So to conclude, we've placed the atoms into the should be flat third band of the Kagome lattice. And this is a really important starting point for studying the orbital frustration that I mentioned to you. And I have a mention of orbital version of spin liquid. This is more of a point for the experts that may be watching, but we're really trying to eventually push towards studying these really exotic and hard to find states of matter. So please, again, I'm highlighting this paper. Please check out our paper. It's very, very interesting. It's an interesting point that we found is that the atoms in the third band, they're not particularly stable. They decay out of this third energy band relatively quickly to being in the other energy bands on a scale of hundreds of microseconds. And so another point for any experts that may be watching is that our experiment is done in this lattice of tubes configuration, right? It's a two-dimensional lattice, which means there's confinement in 2 dimensions, but there's not in the third dimension. And so the interactions between the particles can actually cause the particles to jet out from the lattice. And so we think that we might see something interesting and perhaps a longer lifetime in the flat band. And so an ability to do another set of interesting experiments by adding another lattice, right? Adding a lattice in the vertical dimension, which will give us this strong confinement. I already mentioned this nonlinearity, aspect, but just, again, just want to relay that, this leads to these interesting band geometry effects, things related to like Berry phase, associated with how you move through the state space of the system. It also leads to interesting points, interesting physics like hysteresis associated with how you cause your atoms to move through the momentum space associated with the lattice, and how that can have a dependence on the direction. Right? And then, a really interesting point, something that I like, maybe, next steps, hopefully soon, is studying this negative J triangular lattice. It doesn't matter so much what that means for the non-experts watching, but know that, this is an interesting way to study chirality, or like handedness, like left hand versus right hand. This is a chiral system. They don't reflect onto each other properly if you think about it. And it turns out that these exotic states of matter have chirality. They can have some sort of chiral symmetry, or it can be broken. And this is a really interesting thing to study. And I think no one's seen a chiral mod insulator yet. And so that would be a cool thing to see. But in the lab now, something really, really interesting that we're doing is developing the ability to arbitrarily control the position of the 2 lattices that I mentioned to you that control the Kagome lattice. So, I mean, I won't spend a lot of time on that unless people ask me about it, but that allows us to do a lot of interesting physics. I'll just say that. And then one thing that's also really exciting, I'm telling you about a lot of exciting stuff, is an upgraded experiment to potassium, right? So aside from doing the science work, I was in a, more of a supporting role for the science work. I'm leading the building of a new experiment where we use fermionic potassium instead of bosonic rubidium. And as I showed you earlier in the talk, the fermions have very different aspects to them. Sorry, I'm kind of blinking. I blinked for a second. But as I showed you in the trap, the bosons are happy to crowd into the same energy state. The fermions are not. And so that sort of automatically should give us some population of our fermionic atoms in the flat band in a way that's very, very stable. And that's a very interesting thing. Okay, and so I'm concluding now. Thank you very much again for the opportunity. I wanted to point out the rest of the Kagome Lattice team at UC Berkeley. This is Zephy. I would what I'm telling you about is his first author paper. It's an incredible paper. He's about to finish up his Ph.D. within the next half year. He's an awesome student, so perhaps some people want to offer him a job. That would be a good idea. These are some younger students that work with me. These are also great students. A transfer student that had some important contributions to the work, and the professor who runs the group, Dan Stanford-Kern, and the sources of funding. Thank you.
Thank you for that great talk. Farah will be moderating the Q&A.
So our first question is, what is the size of the lattice spaces and how many atoms are in each lattice space approximately?
Yeah, the lattice spacing is a few hundreds of nanometers, something like this. And the number of atoms, our Bose-Einstein condensate is typically like 50,000 atoms or so, 50 to 70,000 atoms.
Okay, and then a follow-up question is, do you think that the different laser wavelengths would allow for the lattice sizes to be different, changing the effective potential the atoms perceive?
Yes, it will, absolutely. So yeah, the lattice spacing it's defined by the two wavelengths and their relationship to each other. So the green wavelength is 532 nanometers. The infrared wavelength is double that, 1064 nanometers. And it's this property together that allows us to make the Kagome lattice. You need this factor of 2. But if you were to keep that factor of 2 and change the wavelengths, absolutely, then you can, effectively shrink or magnify the lattice.
Okay, and then we have a question from a professor in a different corner of physics. He says, thanks for the nice talk, interesting stuff presented effectively to a broad audience. I was indeed wondering if you could run the experiment of the Kagome lattice with the fermions. Is the comparison interesting? Yeah.
Yeah, no, that's an excellent question. That's exactly what we want to do. So I can tell you that my postdoc advisor is incredibly excited about putting fermions instead of bosons in the Kagome lattice. Perhaps one of the most interesting things about this, the statistics are different, right? I mentioned that the fermions don't like to all be in the same energy state. That adds a very unique element to the Kagome experiment. But also, I mentioned how in our experiment, we see the atoms being in the flat band as being unstable. They don't last in the flat band for very long. And that's where we want them. That's where a lot of the interesting physics associated with frustration that leads to the exotic states of matter will be. And so ideally, we would have our atoms in the flat band for definitely longer. I don't know how long, but we want them to be there as long as we want them to be there. And so one way to achieve that is by using fermions, right? Because fermions stack themselves up in these energy levels, the fermions can be made to stack themselves up right into the third band, right? And that is, the fermions stack themselves up to the Fermi energy, right? And so, if you can make that stacking overlap appropriately with the third band, then you just have fermions in the third band. That's just what it is. And that provides potentially interesting direction for us to pursue this physics.
For some of your future work, how long will it take to set up the lab to be able to make the observations or measurements you would like to make? What's the total cost of such a system? Any idea?
Yeah, good question. The time, that's a tough one. It depends on a lot. So, I didn't tell you anything about how we do all this stuff. The community knows how to make a Bose-Einstein condensate, but it's a very finicky process that takes a lot of parts and requires a lot of physics, a lot of different subsystems to be working correctly. So to build a new experiment that has a BEC or sort of fermion equivalent, degenerate Fermi gas, can take anywhere from 2 to 3 to 5 years before, like, coming from an empty lab to producing science. As far as how much they cost, a lot. Building an experiment like this from scratch is about $1 million, something like this. A little less than that. But I would say that if I were to start my own lab, anybody watching, I would definitely need about $1 million, $1.5 million to do this.
You mentioned stability and time issues with your experiment. What is the time scale that this experiment is happening in?
So the entire experiment lasts 40 seconds. So that is from these really hot rubidium atoms coming out of a relatively scorching oven relative to the final BEC temperature, through all the parts of slowing them down and cooling them, to putting them in the lattice, to flashing off the lattice and taking an image. That takes 40 seconds. So in our measurements, what we're doing is we're running that 40-second process over and over again, effectively making identical copies of the BEC and putting them into the lattice. And that's how we study our data. But the actual science part of the BEC going into the lattice and then taking an image, that's something like a millisecond of that order.
Following up on the question of number of atoms per lattice point, you talked about your BEC with I think you said around 50,000 atoms. Is that spread across many lattice sites?
That is spread across many lattice sites. That's right. Yeah. I was just giving you the number of the total number of atoms in the BEC before we throw them into the lattice.
And could you explain the colors in your band structure plots?
Yes. Which band structure plots? The ones from the real data, or I showed a schematic, like a cartoon one-dimensional version. So
specifically the one that showed off the flat band in the Kagome lattice.
Yeah, let me actually, is it okay if I share my screen again?
Yes.
Great. Okay, that didn't work. Sorry, 1 second. This one. Okay, I think this is the right slide. So is it this one with the band structure? Was it what these colors mean?
Yes.
Okay. These colors are referring to a band. So we had to do some, processing of the data, and the bands are just meant to show a certain uncertainty range of what the momentum was for that measurement of the curvature or the local slope of the energy band. So it turns out that this is a really cool method, the displaced laser method, to impart a momentum to the BEC. Very, very cool, and it works nicely, and it was great for us. But it is not the most consistent way to initialize your Bose-Einstein condensate into a particular momentum. So there's some fluctuation associated with that, and the blue tells you about the size of that.
Okay, and I think that's all the questions we have. Okay, there's one in the, I was thinking figure 1 from your preprint, in fact, from one of your early slides when you first showed.
Okay, yeah. Those colors were just shown, that we're just trying to make some distinction between the bands. And so when you look at that figure, I can, maybe I'll go to it one more time. Yes, there we go. All right, so I believe the question was about this this color scheme. These are just showing the different regions, the different bands. So the colors are showing the just different energy bands. It's just meant to be like a sort of illustrative thing. I guess highlighting the fact that when you make the lattice depth non-zero, so when you actually give some strength to the binding of particles to particular points, you get the separation between this set of energy levels and this set of energy levels, giving you these energy bands in the different colors.
And then the last question, what is the real space size of the lattice in millimeters?
The lattice spacing is a few hundred nanometers. So something like, so I showed this image here. Let me share my screen one more time. All right, so yeah, on this slide, I'm showing you a calculation of, given the interactions that we have in our system, what the real space configuration of the lattice looks like. That is what this is on the right. And you see that the spacing between the regions where the atoms are is about, 350 nanometers or so. So this is the scale of the lattice. The lattice spacing is a few to several hundred nanometers apart.
Okay, thank you so much for all your questions. And thank you, Dr. Brown, for answering.
Yes, thank you. This is great. Super happy to be here.
Yeah, thank you so much.